Hello, everybody. We're going to build confidence intervals today. How do I know that? Well, when a question states build the confidence interval, I think it's pretty straightforward. So, what do we have here in example 1? The drug J14 has reaction time standard deviation of 4 minutes. We sample 120 users of this drug and we find the average reaction time to be 8 minutes. All right. So in this first example, I want to take it nice and slow and kind of build up everything. Because when it comes to confidence intervals, I go to my formula sheet, and you see there are 3 confidence intervals, 3 very popular confidence intervals when you're dealing with one sample. You could do a confidence interval for the average, standard deviation known, confidence interval for the average, standard deviation of the population not known, or confidence interval for the proportion. These are typical 3 confidence intervals when you have a single stream of data. And so which one do we have? Let us go back. Do we have the sample standard deviation or population standard deviation? Part A. Well, that's actually the biggest question when you're building a confidence interval, is knowing whether you have a sample or a population standard deviation. And in this case, as I read that top sentence, the drug has a reaction time standard deviation of 4 minutes, I have to believe that came from the company. And since that came from the company, tells me the sigma of 4. So I see that we have a population standard deviation. And once I know it's a population standard deviation, that really narrows down. Once I know it's a population standard deviation, I know I use the Z distribution. If I did not know the population standard deviation, I would use the T distribution. That's how they're paired. If I know sigma, I use Z. If I don't know sigma, but I know S, I use T. And so we go back here, I'm going to use the Z since I have sigma. And in fact, when I build a confidence interval, I'd like to know all my letters for the confidence interval. There's not many. All right, for a confidence interval, you need X bar, you need Z, you need sigma, and you need N. Those are the 4 letters of the formula. Once again, back to the formula. I would pause the video right now and take a picture of each one of these, take a picture of the screen and utilize it. All right, so we're back. So the formula has an X bar, a Z, a sigma, and an N. So X bar, what is that? Well, by definition, it's the sample average. We'll read the second sentence. We sample 120 users, and we find the average reaction time to be 8 minutes. Got it, 8 minutes. Now let's go back, make sure we understand the question. We want to build the confidence interval for the true average reaction time. See, what we're doing is we're going to use our sample to build a confidence interval that will place 90% of faith in this confidence interval in the true average reaction time. Let's say we don't actually know the true average reaction time, but we have 120 users to sample from. From these 120 samples, we can build a interval for which we believe the true average reaction time would be in 90% of the time. So let's see, how would you build it? This way. So sigma, again, is given, it's 4. N is given, that's the sample size. You have to know your letters. If you know your letters, it's easy to build confidence intervals and to do a hypothesis test. You really need to have flashcards or some type of way of memorizing these letters. So N is sample size, sigma is the standard deviation of the population, X bar is the average. Really, the only thing of discussion is the Z. How does one find the Z value? Well, it's all based on the confidence level. You see, when you're building a 90% confidence interval, so let's go to a picture for example 1. So for example 1, we want a 90% confidence interval. So what that means is when I build my normal picture, I want 90% inside. This is the Z we're talking about. The Z value, which bounds the middle 90%. Good thing is we learned from previous videos how to do this. I would, first of all, figure out this area to make sure we're clear. That's 5%. How would I get that? Well, because of symmetry in the normal picture, I know that both sides are equal. And if 90% is in the middle, that leaves 10% outside and 5% on each side. Why do I care about that? Because in Excel, remind yourself in Excel needs to know the area below the Z marker. The area below the Z marker, and Excel will do the integration to figure out the actual Z value. I want to make sure it's clear to you why I'm utilizing 95% in my formula, because it's the area below the marker. 90% confidence has 95% below it for the Z marker. And so when I go up here, I'm going to use norm.s.dist. Actually, I'm wrong. Norm S inverse, because inverse, and that's how I would know is the probability word. When I open up norm S dist, it'd be looking for a Z value. Well, I don't know the Z values. Norm S inverse says, you give me the probability, I will find the Z value for you. And that's what we're looking for. So I'm going to enter in 95% because that's the Z value area underneath we're looking for. We're looking for the Z value whose area underneath is 95%. Norm S inverse is how we'll build that. And now I have the 4 letters. According to my rules, and these are the rules I like to do for confidence intervals, I like to pick the correct formula. I did. Pick the T or Z and tell me which one you picked. I picked the Z because I knew the standard deviation, the population standard deviation. Find the appropriate values. I did that. Now it's time to find the margin of error. And that will be UB at the end. Find the margin of error. So let's get back to our example. The margin of error, MOE, the margin of error. Well, the margin of error by definition is always the right-hand side of the plus or minus. That's true for all 3 of these formulas and pretty much any confidence interval formula. The back half is known as the error. It's always your point estimate plus or minus the error. Because you imagine you're going to build the center of your confidence interval based on your sample average, and you're going to use a little wiggle room, the error. Same idea. I'm building a confidence interval for the mean. I'm going to use my sample mean as a nice center and use plus or minus this error. And that's what we do when we build confidence intervals. We use our sample average as the center, the point estimate, and then we use the error for the plus or minus to build how wide the confidence interval will be. Sorry. Margin of error. So the formula for the margin of error was Z times sigma divided by the square root of n. So that's the formula, and I'll pause there to make sure you see it. Actually, let me enter it, and then I'll allow you to pause the screen to see and make sure it makes sense that we are using Z times sigma divided by the square root of n as part of the formula. So there's the margin of error. From the margin of error, we could build the lower bound and the upper bound. Well, the lower bound will be the sample mean minus the margin of error. You take off the margin of error to get your lower bound of the confidence interval. To get the upper bound of the confidence interval, we take the average, the point estimate, your sample, and add on the error. This forms my confidence interval. So we've done part C, build the 90% confidence interval. So that's what this would be, the 90% CI. Now, of course, after I'm done building, I always like to have my conclusion. So from this confidence interval, my conclusion for this confidence interval, so what would that be? That would be part D. My conclusion would be I take charge. I built this. I am 90% confident, because that's what you are. I am 90% confident that the what? Always articulate what you're trying to say. That the sample, bullcrap, you know where the sample is, you built the sample. That the population average reaction time is between, and then you state it, the LB and UB. I'm being short there, but you should be putting in there the actual numbers. I am 90% confident that the population average reaction time is between 7.4 minutes and 8.6 minutes. That's very important. So this is important for people putting directions on medicine, right? The average reaction time, or the average cure time, the average cooking time, the average storage time, whatever you're looking for. The average time between is 7.4 and 8.6 minutes. Could it be outside? Of course it could be outside. I'm 90% confident that the average time is between those two lower bounds. I'm not going to be 100% confident because that's impossible. To be 100% confident, I would actually need to know what the true average is. If I don't know the true average, then I actually have to do a sample, and the sample means there's some chance that I'm wrong when I take everything. So I'm 90% confident, and I'm okay with that. Now, what happens if we build the 95% confidence interval? What would happen? Well, let's build it and see what happens. 95% CI. When I first build confidence intervals, I like to look at the differences between a 90% and a 95%. Well, the average is still the same. The sigma is still the same. And the n is still the same. The margin of error formula doesn't change, so I can copy that over. The lower bound and upper bound formulas wouldn't change because they're just formulas. You bet it. You guessed it. The only thing that changes when you build a 95% confidence interval is the z-value. This is the only thing that really directly affects the confidence interval. Now, how would I do the confidence interval here? How would I find the z-value here? Let's think about the question. It's a 95% confidence interval. I will not put in 0.95. I have to think about 95% is for the middle. So how much is there left on one of the edges? You guessed it, 2.5%. That's how much I'm adding to the 95% to get 0.975. I need you to think about that, okay? 95% is the confidence interval. That's what's in between. That leaves 2.5% on both sides. If I take 95 and 2.5, I get the area below the z bar in the picture we've drawn before. That makes 97.5. And so just like that, my formula adjusts and I create my part E, my 95% confidence interval. And then part F, though it's not labeled, I can make my sentence. I am 95% confident that the population average reaction time is between and now you restate your numbers. In the case of 95%, it's 7.2 to 8.7. This is very important to see. For a 90% confidence, your bounds go from 7.4 minutes to 8.6 minutes. If I want more confidence, look what happens to the bounds. If I want 95% confidence, look what happens to the bounds. They get farther away. Why is that? Well, because you have an error that's bigger. But why is the error bigger? Let's go back to the formula. Here is the formula we've been using for confidence intervals. I state the error got bigger if the confidence went up. Why? Well, which one of these four letters, X bar, Z, sigma, and N, is intimately tied with the confidence interval? You guessed it, Z. If your confidence goes up, your Z gets bigger. All right? If your confidence goes up, your Z gets bigger, which means what you're multiplied by gets bigger, which means your error gets bigger. And if your error gets bigger, your interval gets bigger. That's the idea I want you to understand. If your confidence goes up, your Z gets bigger. If your Z gets bigger, your error gets bigger. If your error gets bigger, your width gets bigger. And that's why I knew I had a wider confidence interval, because I wanted more confidence. And that's example 1. All right, let's pause now and let's try example 2. All right, we're back. Example 2. Well, example 2 is more of a theory question. So what do we have here? We have a 95% confidence interval. By the way, CI is my abbreviation for confidence interval. Should have said that. For the mean salary of a graduate is between these two numbers. The population standard deviation used for this study is 11,000. So it's very important. They gave me sigma. All right, that's very important to me. They gave me sigma. That means we're using the Z distribution. So these statements up here are still true for this question. I can bring those down. And I'll give myself a little bit more space in here. Insert. Make that UB. UB. What is the point estimate of the mean salary for all graduates? So what is our point estimate, better known as our X bar? Our point estimate is a fancier phrasing for the sample average, the point estimate. And the reason they utilize that language is because if I'm trying to find an estimate for mu, what would be a great point estimate for the true average? I hope my sample would be. I hope I did a good representative random sample so that would be almost spot on with the true average mu. X bar is a sample average. I'm hoping it's really close to the true average. All right, so what information is given in the question? The population standard deviation is known, 11,000. All right, so sigma is 11,000. It says the confidence interval is 36,000 to 43,900. I'm filling in the information I know. I want X bar, okay? How would I get X bar from this information? Well, you have to understand truly how to build a confidence interval if you truly want to understand how to find the point estimate. A confidence interval is what again? A confidence interval, by formula, is X bar plus or minus the error, okay? A confidence interval is X bar plus or minus the error. So X bar will always, period, be in the middle of your confidence interval. So I know exactly where my where my center will be, X bar. It'll be right in the middle of that confidence interval. So right in the middle of that confidence interval is my center. So how would I find that? There's a bunch of ways to do it. The way I choose to do it is I'm going to take the average of those two numbers. So if I take the average of these two numbers, I'll get the number right in between them, 39,950. And so that's my point estimate. Think about it. I have a low value, the high value. The average of the two would be directly in the middle, which would be the mean in this case. X bar will be in the middle of the lower bound and upper bound, period. Now that I know the X bar, that means I can actually find the margin of error now. Think about that. If you know X bar, you can find the margin of error. All right? Because if you have X bar, the average, then the margin of error should be, think about this, the lower bound. If I take the X bar minus the lower bound, I should get the margin of error. What's my formula? For some reason, it feels like I did it wrong. So if I take my X bar and take off the lower bound, we get the margin of error. Same thing. If I take the upper bound and take off the X bar, I also get the margin of error. So it's a way for me to verify that I did do the math correctly when I did the average. This is all about understanding how to build a confidence interval right here. Again, halfway in between, right in the center of your confidence interval will always be the sample mean. It will not be mu, the population average. We have no clue where the population average is. If we did, why would you build a confidence interval? If you knew exactly the average salary was $42,000, why are you building a confidence interval that says 95% chance? You would say, no. I know exactly what it is. It's 42,000. So you don't know the true average. So you're building a confidence interval to try to capture the true average. What you do know is your sample average is right in the middle of those two. And how do you find the middle? Well, you would average. That's what you would do, like I did. Once you know the average, then you know the distance from the average to each bound. It doesn't care which bound you're doing. The average to the bounds, whether it's lower or upper, better be the same because that's the margin of error. The margin of error will always be the difference, the distance, whatever you want to call that, from the average to the lower bound. Again, I'm just utilizing the formula. All right, let's fill in the Z. How did one get the Z? Well, again, it's a 95% confidence interval. So the norm.s.inverse, 95% leaves 5% outside, 2.5% for the lower tail. So I'm going to use 0.975, just like the example one's explanation. The good news, after you do enough of these, you start memorize the fact that for a 90% confidence interval, it's 1645. For a 95% confidence interval, it's 196. These are the two most typical confidence intervals you build in life, the 90 and the 95%. All right, these are the most typical ones you build. So after a while, you just know it's 1645 and it's 196. All right, these are, and sometimes in formulas, people just put those in there without teaching you why 196 just pops out of nowhere. It's because of the truth of the calculus behind these that is stored in the norm's inverse. All right, so I have all of this information out there. And all of it has been deduced from the fact given. I'm just working on the fact that I had a 95% confidence. That's how I got that. The point estimate, again, is the center of the confidence interval always. That's not where mu is. I don't know where mu is. I just have a 95% confidence. It's somewhere in between those two numbers, the lower and the upper bound. That's all I have confidence in. It's somewhere between there. Don't know where it is, but it's somewhere between there. How would I find n? Well, let's think about this. I know, for example 2, I know the error, the margin of error, is z times sigma over radical n. How do I know this formula? Because I've been preaching it for 20 minutes now. That is, the error is always the back end. The error is z times sigma over radical n. But I know a few of these pieces in this example. I know the error, 3950. I know the z, 1.96. I know the sigma, 11,000. I do not know radical n. So now this is an algebra game. I like to pause right now, and I want you to see if you could do the algebra needed to solve this problem. All right, welcome back. So what would I do? Well, first thing, I'd clean up the right-hand side by multiplying the 1.96 by 11,000 to get 21,560. So I get 21,560 on the right-hand side times 1 over radical n. Or you can put the 21,560 in the numerator if you so choose. So now I want to solve this. Well, to solve this, I'm going to multiply both sides by radical n. What I'm doing is I'm moving the radical n from the denominator. I'm cross-multiplying, if you like to call it that. So I'm cross-multiplying. And I'm having troubles writing that number. So all I did was I multiplied the radical n over. All right? I multiplied the radical n over. Now, I'll divide the 3950 the other direction. And then me and my calculator will get this number. So 21,560 divided by 3950 gives me a whopping 5.46 to 2 decimals. 5.46 to 2 decimals. Well, if radical n equals 5.46, how does one get n? You betcha. Square both sides. So squaring that number, and since I already have the long number stored in my calculator with no rounding, I'm going to use that. So I'm pleased. I'm using the unrounded number in what I'm about to do, not the 5.46. I'm using the 5.48227 in my TI calculator. Squaring, I get 29.79. So N is roughly 29.79. Now, yes, how do you have 29.79 patients? You don't. You would typically round up to ensure you have your confidence that you're looking for. So in this case, my answer would be 30 patients, 30 customers, 30 cows. I don't know, depends on what we're studying. All right, and so I have to go back to my question. But the answer for part B, determine the sample size, I need 30 people in my sample size. I need 30 graduates. So this would be for part B. The point estimate would be, part A would be XR. So, one more time as a quick review. If I want the point estimate is the sample average, X bar. That is in the middle. How do you find the middle? I don't know. I would average these two, and that would give me the middle. Once I have the middle, everything else comes falling down. In order for me to find the sample size, I need all the rest of the pieces, Z, sigma, and error. Because of the formula, error is right here. If I know the error, Z and sigma, I could definitely solve for N, and that's what I did in this formula. I utilized the fact that I knew this. The error is Z times sigma over radical N. And I just plugged in the numbers I can know, and then I did algebra to solve for N. All right, guys, that's example 2. All right, your turn now. Once again, right? Your turn. Pause the video. See how you do with example 3 before I get back. All right, we're back. Example 3. One more time. Hit me, baby. What do we got to do here? I like to go to my question first. Build the confidence interval, 95%. Got it. Which one is it, though? I have 3 of them. Well, build the confidence interval for the population average. Average. That means it's one of the first 2 formulas. Average. Confidence interval for the average. Confidence interval for the average. It all depends, am I using sigma or S? Because that'll make my decision. Which one of these formulas? That's why it's my first step, is deciding which formula makes sense. And honestly, it comes down to my second question. Is it sigma or S? What do I have? Do I got the population standard deviation, or do I have to use the sample standard deviation? That's the difference in the letters. Sigma is for population. Greek letters are for population. S, American letters, are for sample. Well, let's read. A recent study has stated that many Americans are skipping on their needed sleep. We decided to test this theory in our town, and so we sample 80 adults and record their average sleep time to be 6.4 hours. Assume the population standard deviation is 1.9 hours. And there it is. Assume the population standard deviation is 1.9 hours. What that means is I can utilize the work I've done up here. That's the great thing, is once you've written the formula once right in Excel, you can paste it down and just got to change the information to get your new confidence intervals. And in fact, in seconds, I can build the 90 and 95% confidence intervals just because I've already built them once in Excel. But I need to know that it was definitely the Z I had to use. And it is a Z that I'm using because I knew sigma. Sigma is 1.9 hours. So I'm changing sigma to 1.9 hours. And notice it did change the margin of error and the lower and upper bound. My N has changed. I have 80 adults. So my N is changing. 80 adults. So that changes my confidence intervals too. I've changed my N, my sigma. I don't have to adjust my Z because my Z is based on my confidence intervals. Notice those are good. A 90% confidence interval, that's your Z. A 95% confidence interval, that's your Z. X bar has changed. Of course, there's a new test. I'm average sleep time in my sample. Read the question. What is the average sleep time in the sample? It says right there 6.4 minutes. 6.4 minutes. That's my new point estimate. That's my new center of my confidence interval. That's very important to me. This is the center of the CI, the point estimate. utilizing the center, and the error I'm going to add and subtract to build my confidence interval. So the LB is my lower and my UB is my upper. I believe with 95% confidence that the average sleep time for this town is somewhere between 5.98 hours and 6.82 hours. And so that's why when I build a confidence interval, I always like to make my conclusion. I am. What's our confidence here? 95%. I'm 95% confident that the true average, it's not about the sample, people. Your sentence should be about the true average, the population average, in this case, the town average sleep is between the two numbers. And let's write it down. 5.98 hours and 6.82 hours. That is my specific answer to this question. Is I am 95% confident that the true average sleep is between 5.98 hours, the lower bound, and 6.82 hours, the upper bound. Excellent. Why is that important? Well, then you can look at part B. Can we conclude that this town is not getting the recommended hours of sleep? Think about part B, the realistic impact. Is this town, wherever this town is this town so stressed because they lost a factory? Are they stressed because a college got shut down and so they lost that? Are they stressed because of COVID hit and they're not getting enough sleep because they're helping their kids out and they're also maintaining their jobs? Are they getting, yes or no, the recommended hours of sleep? The answer is for part B. So for part B, my answer for part B is I don't think so. I don't think they're getting the recommended hours of sleep. So can we conclude that they're not? Well, with 95% confidence, I can conclude they're not. Notice 7 is not in the confidence interval. 7 is not in the CI. So I have high confidence, 95% confidence that is, I have high confidence that the town is sleep deprived. Now we can talk about what do we need to do to get this back to normal. What does this town need to do to get back to normal? We know the town is not getting the recommended hours of sleep. This is not good. So what could we do to offer up a way so they can improve the hours of sleep they're getting? This is the reason we build confidence intervals, so we can make statements like this that go against the national average. This town is clearly, with 95% confidence, going against the national average, because the national average is 7, and 7 is not in that confidence interval. That's the key. 7 is not in that confidence interval. If it was a number in that confidence interval, I would say, nah, they seem good. They're in the interval, so who cares? But because they're not in that interval, we are having issues. In fact, this confidence interval is lower than the national average. That's the key to me. This confidence interval is lower than the national average. So that's why I'm saying they're self-deprived. Ha, I must be self-deprived too, because they are sleep-deprived. Sorry, they are sleep-deprived. They might be self-deprived too, but they're definitely sleep-deprived, not just self-deprived. All right, guys, one last thing to note. In each one of these intervals, I used the Z distribution. In my steps, and I need to add that to my steps, what gave me the right to build the confidence interval for each one of these? Each one of these used the same confidence interval. What right did I have to build the confidence intervals? I kept saying normal. What right do I have to use normal here? What right in each one of these do I have to use normal? I'm pausing because I want you to see it. What right in example 1, 2, and 3, it was the same answer for each one of them. It didn't say normal. I don't think I said normal anywhere. I didn't say in example 1, drug reaction time was normal. I didn't say in example 2, graduate salaries are normal. And I did not say in example 3, sleep hours are normal. They may be, but how do you know? The answer is you don't care if what? If n is greater than 30, greater than or equal to 30, we get the central limit theorem and we get normal for free. That's my final point of interest here, is I get normal for free in each one of these because my sample size is greater than or equal to 30. Notice in each one of these examples, all right, the sample size was greater than or equal to 30. If it was not, you would have to verify, and you could check out my video on checking out normality. You'd have to verify normality before you could build these confidence intervals. All right, guys, thank you very much for watching this video. I hope you stay tuned for future videos.